Hello students, good morning. Now we are doing the next part of the chapter, that is ionization energy. Okay, we have did the practice of the Z effective, that is effective nuclear charge. Okay, now we are going to discuss about the ionization energy. So what is ionization energy? It is the energy which is required to remove, suppose this is the atom, okay, and here the electrons are present, okay. So what happened that if we are going to remove the outermost electron, how can outermost electron be removed? Definitely electron will absorb some energy and then go to the higher excited state. Or if electron will given such type of energy that it will absorb that much sufficient amount of energy that it will go to infinity, then in that case the atom get converted into the ion, and this energy is called ionization energy. So to remove an electron from isolated gaseous state, now one thing is there, atom cannot be removed from the solid state. So that's why first of all the atom, suppose this is X atom, it is in solid state, so we are giving it sublimation energy so that the atom get converted into the gaseous state. Okay, now after gaseous state it is also neutral also, we will provide the energy, and due to that energy, like this is ionization energy, the gaseous atom get converted into the ion, and this required amount of energy to remove an electron from the outermost valence shell of a gaseous isolated atom, it is called ionization energy. So students, you have to remember this, that what is ionization energy? Energy required to remove an electron from the isolated gaseous atom from its valence shell to convert it into ion. Now one thing, it is clear to us that ionization energy is endothermic. Why? Because electrons are going to absorb the energy, they are not going to release the energy. So the ionization energy is endothermic. Okay. Second thing is that what is the unit of ionization energy? The unit of ionization energy is kilojoule per mole, or we can say it is electron volt per atom. It may be electron volt per atom. Okay, so these are the some relation, some unit of ionization energy, this much. Okay, now there are certain factors. Now we will discuss about the next part of ionization energy, that is successive ionization energy. What is successive ionization energy? The energy which are continuously given to an atom to convert it into the ion. Okay, so let's discuss. Suppose this is a metal and it is given the ionization energy. Suppose this is ionization energy 1. First time we are giving. That's why from the outermost shell, it is in gaseous state, it will remove electron and it will convert into M plus, and suppose it has removed one electron. So it is the first ionization energy. Now again, if we are having the metal ion, okay, and we again want to remove one more electron, then in that case what happen, we will give again the ionization energy, it will give form the ion M2 plus and remove one electron. Okay, since we know that the size of metal atom, it is quite larger, okay, means whatever the size we are giving the ionization energy, it is going to remove electron. But next time in M plus, we know that the effective nuclear charge is more as compared to the number of electrons present, because number of electrons are comparatively lesser as compared to number of protons. So that's why we are giving large amount of ionization energy to remove electron from an ion. Okay, again we are having M2 plus. and we are again, if giving the ionization energy, then we have to give more amount of ionization energy to remove again from the metal ion having more Z effective. So we are giving here ionization energy 3 m 3 plus electron. In this case, let's take the example of sodium. Suppose sodium is having the electronic configuration 1s2, 2s2, 2p6, 3s1. So initially we are going to remove an electron from the outermost valence shell. It will be easier. Second time we will see that the configuration of this one will be 1s2, 2s2, 2p6. So continuously the size is decreasing, due to which why size is decreasing, because in this 1s2, 2s2, 2p5, in this 1s2, 2s2, 2p4. So continuously the size is decreasing. Why? Because the effective nuclear charge is increasing. That's why the successive value of ionization energy for a particular atom, it is always more. For a particular atom, the third ionization energy is always more than second ionization energy, than first ionization energy. So you have to remember. For example, if we are having an example F minus, sorry, F plus 2. So that means which ionization energy will be more? This one is first, this one is second. So second ionization energy for formation of F plus 2 is greater than first ionization energy, that is formation of F plus. So you have to remember that for a particular type of atom, always for a particular atom, for any particular atom, the value of ionization energy always decreases, means increases. That means we can say the third ionization energy is more than second and then first. Now there are certain factors which affect the ionization energy. So the factors which affect the ionization energy are: number one is atomic radius, or we can say the size of atom. So the size of atom or atomic radius is one of the factor which affect the ionization energy. Ionization energy is actually inversely proportional to the atomic size or atomic radius. Why is it? Because if the atomic size increases, then we have to give lesser amount of energy to remove the electron. That's why on increasing atomic size, the ionization energy will decrease. Second one is the effective nuclear charge. It is the effective nuclear charge, that is we can say Z effective. So the ionization energy, it is also directly proportional to Z effective. If we will increase the effective nuclear charge, means the size of atom continuously decreases, then in that case the ionization energy will also if the size of atom decreases, then the Z effective will also increase, and in that case the ionization energy will increase. Suppose we are going from left to right in a periodic table, so continuously the atomic size decreases. Why? The Z effective increases, and hence the ionization energy will also increase. Third one is the screening effect. Or shielding effect. Okay, that is called. So the ionization energy is inversely proportional to the screening or shielding effect. As much as the screening effect or shielding effect increases, then we will require lesser ionization energy to remove the electron from the atom. Fourth one more is there, that is called penetration effect. What is penetration effect? Penetration effect means it is related to the shielding effect. Means what amount of repulsion force is means what amount of attraction force is applied by the nucleus on the outermost electron, in the presence of SPDF subshell. If F subshell is there, then the penetration effect will be lesser. Okay, why is it? Because the F orbital is having a poor shielding effect. That's why the nucleus will be able to attract the electrons from the outermost shell. So penetration effect means how much the orbitals are actually covering the nucleus to means so that the effect of nucleus is not penetrating to the electron. Means attraction force must not penetrate through them and reach to the outermost electron. So it is just like the shielding effect. So penetration effect S, P, D and F, they are having, this is the order of penetration effect, and you know this is also the order of shielding effect for the orbitals. Fifth one is about the electronic configuration. This is very important. So what about electronic configuration? We are having two type of configuration. That is, number one is half filled orbitals and second one is full filled. So you have to remember that half filled orbitals is always having more ionization energy, or full filled orbitals, they are having more ionization energy as compared to the other configuration. Why? Because half filled and full filled electronic configuration are quite stable. Okay, they are stable, so the atom do not want to release the electron easily from their stable configuration. Like you can get the P3 configuration outermost, or D5 or F7 configuration. These are the outermost configuration, that means they are half filled. Full filled means P6, like D10, like F14. These are the fulfilled electronic configuration. Now let's discuss about the trends of ionization energy. That what is the effect of ionization energy on moving in a group or moving in a period. So let's discuss first of all like in a period. So in a period from top left to right, we know that the atomic radius, it will decrease. That's why the ionization energy will increase. So let's start with 1, 2 periods. Okay. So you can write it by yourself also, like among hydrogen and helium. This is period number 1. So it is having 1s2 and it is 1s1 and it is having 1s2. So it is having, one thing is there, it is having fulfilled configuration, it is having half filled. Among half filled or full filled is more stable. Okay. And one more thing, that left to right atomic size will also decrease. That's why ionization enthalpy increases. You have to remember that helium is alone the metal having highest ionization energy in the period. Second, again we will start with this one was the first period, then N is equals to second period. Like lithium, let's start with the lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So which is having the highest ionization energy? Let's write down the configuration. Lithium 1s2, 2s1, then 2s2, boron 2s2, 2p1, carbon 2s2, 2p2, nitrogen 2s2, 2p3, oxygen 2s2, 2p4, fluorine 2s2, 2p5 and neon 2s2, 2p6. So what is the trend actually? The trend is on moving from left to right, the ionization energy will increase. Why? Because the atomic size will decrease. Okay, atomic size will decrease, Z effective will increase, that's why ionization energy will decrease. So the ionization energy will be like this. Okay, so continuously the ionization energy must increase, but actually we must know that these are like 2s2, 2p3, means these are this is the fulfilled s orbital as well as this is the half filled p orbital, and we have studied that half filled and fulfilled configurations are quite more stable. That's why the order of ionization energy will be actually somewhat little bit changed, and it will be like this. The answer will be the ionization energy of beryllium is more than boron, and ionization energy of nitrogen is more as compared to oxygen. Why? Because nitrogen is having half filled configuration than oxygen. So that's why nitrogen is a little bit more stable as compared to oxygen, and that's why it is more stable. So this will be the order of ionization energy of elements in second period. And so on. In the same way, you can write the order of ionization energy of different element in different period in the same way. Now let's discuss about the ionization energy in a group. So all the groups, means group number 1, 2, 3, 4, 5, all the groups are having the means top on moving from top to bottom, the value of ionization energy will decrease. Like let's take with group number 1. First group is there, that is hydrogen. We are not considering lithium, sodium, potassium, rubidium, cesium, francium. So top to bottom moving, the value of ionization energy will decrease. Why? Because atomic size will increase. Same in the second group, the value of ionization energy will decrease from top to bottom because the atomic radius will increase. Now let's come on group number 13. This is the exception. The group number 13 and 14 shows the exception, and that are important. The group number 13 is boron, aluminium, gallium, indium, thallium. Okay, these are the elements of group number 13. The expected order of ionization energy must be like this, that top to bottom, but it is quite wrong. The actual order is of group number 13 is, actual order is boron is having maximum ionization energy, then tellurium, after that thallium, after that it is of gallium, after that it is of this one where aluminium, and after that it is of indium. So this is the actual order in which all the order is completely disturbed. Why is it? There is a certain reason behind this. And what is the certain reason that we have to learn? First thing is that you know that since thallium is at the base, so it must have the lowest ionization energy, but it is not. Why is it? Because due to the presence of f orbitals, okay, we have studied about the lanthanoid contraction. Due to the presence of f orbitals, the screening effect is very lesser, due to which the z effective is very more, and due to which the size of atom continuously in lanthanoids decreases, that these elements get a very lesser size as compared to the other element. So this is having the means here the order is disturbed due to the lanthanoid contraction. This is the reason. The lanthanoid, due to lanthanoid contraction, the order is disturbed. The thallium is having lesser atomic radius as compared to others. And the gallium, let's discuss about the gallium. Why gallium also is having lesser? This is due to the fact, due to here the aluminium is having more size as compared to the gallium. Why is it? Because gallium has d orbitals, and due to the transition contraction, means the d orbital, presence of d orbitals also shows the lesser screening effect. That's why the z effective will be more, z effective will increase. So due to transition contraction also, the gallium is having lesser size as compared to the aluminium, lesser we can say more ionization energy as compared to the aluminium, because if size decrease then the value of ionization energy will increase. So its size is very lesser as compared to the others. That's why its ionization energy will also increase, and this is the order. And among group number 14, like carbon, germanium, here again also in these both elements, means top to bottom, the value of ionization energy must decrease. But here again, due to the lanthanoid contraction, again the order is disturbed. And in all rest of the groups, you will see that you are getting the particular same type of order of ionization energy, that is increasing from left to right and decreasing from top to bottom. So this is all about the ionization energy.